In the previous lesson, we finished up by exploring a problem in 2 dimensions that had 2 parts, an x dimension part and a y dimension part. But what I didn't say was that that problem was actually an introduction to a type of problem known as a projectile motion problem. In this video, we're going to learn how to work projectile motion problems in 2 dimensions, even more complicated than just horizontally launched projectiles. And the first thing to start off with is probably a definition of what projectile motion is. Projectile motion is simply free fall. Okay, and we know that free fall happens because gravity is a y-dimensional force. So free fall is always going to have y-dimensional motion as a component. But in addition to that, projectiles are able to also have x-dimensional motion. So the object is moving at a constant speed in the x dimension because there's no gravity accelerating that object, but it is free falling in the y dimension. It's important to note what's not included in this definition of projectile motion. Notice that air resistance is excluded. The only force is gravity. Free fall in the y dimension says the only force that's acting on the object is gravity, and air resistance is neglected. Now, it's really important to note at this point that in the real world, air resistance usually can't be neglected with projectile motion, because projectiles usually either are beginning by moving very quickly through the air, or by the end of their motion, they're moving very quickly through the air because they attain such high speeds with acceleration due to gravity. Acceleration due to gravity is a very fast acceleration, so therefore things are going to speed up in short periods of time. So we do make an assumption with projectile motion that air resistance is negligible. We're hoping that our object is either very aerodynamic or that our time frame is short enough that the object's not going to accelerate to too great a speed. Or maybe another way of thinking about this is we're just modeling what the effects of just gravity on the object are. But if we want a more complete model, we would have to take that to the next level and add in air resistance. The problem is that we can't do that easily with the mathematical tools that we have. Air resistance is a very, very complicated force and causes very, very complicated effects on acceleration. And it's just too difficult for us to deal with here. So we're going to define projectile motion as not being affected by air resistance. Okay, let's take a look at a problem involving projectile motion. Here we have a base jumper, base being an acronym standing for buildings, antenna, spans, and earth, like cliffs. And spans are like bridges. So these are people who jump off of tall things as a hobby. I would not recommend it. Actually, this is pretty dangerous because they're so close to the things that they're jumping off of. It's not like skydiving. We're up in an airplane and there's really nothing nearby for you to collide with. These people who do base jumping are really close to the objects they're jumping from, and accidents happen frequently that can be fatal. So a base jumper sprints at 24 kilometers per hour as a full speed sprint toward the edge of a cliff, then leaps horizontally into the air, deploying a parachute 3.22 seconds later. This must be a very, very tall cliff for the base jumper to be able to fall for 3 seconds and then deploy a parachute. What is the displacement of the jumper from the edge of the cliff when the parachute deploys? Okay, so we're looking for the actual straight line distance, not the curvature distance, but the straight line distance from the point where the jumper jumps off of the cliff to the point where the jumper is 3.22 seconds later. How are we going to figure this out? Well, this is the easiest type of projectile motion problem because we have a horizontally launched projectile. This person is running and just jumping horizontally off of a cliff. It's going to look something like this, okay? Notice that in the x dimension, we have a constant speed. There's a constant separation between these points in time. And then in the y dimension, we have acceleration happening. The points are spreading out for each time interval that goes by. And the time interval between these points is the same. So we see that the object is speeding up in the y dimension, moving at a constant speed in the x dimension, as we would expect for these types of problems. Let's make a table that shows what we know, and we're going to adjust some of the values that we know right away. Do we know the original x and original y values? Well, I'm just going to set both of those to 0. So we're just going to say that this base jumper starts at 0 meters in the y dimension, and then our final y position, or vertical position, is going to be negative because it will be below the starting point. The final x is unknown. That's what we're looking for. Same with the final y. We need the displacement from the edge of the cliff, so we're going to need to calculate how far this cliff diver moves in the x and the y dimensions. Now, do I know the original x velocity of our base jumper? Yes, I do, 24 kilometers per hour, but I also know that I'm given a time in seconds, 3.22 seconds, and I know gravity in meters per second, not kilometers per hour, meters per second squared for gravity. So I need to change kilometers and hours to meters and seconds before I use this value. Let's go ahead and do that unit conversion. So I'm going to start by writing out my 24 kilometers per hour term with the unit label spread out. And then I'm going to multiply this by a series of conversion factors to change it to meters per second. First of all, let's get rid of kilometers. So I'm going to multiply by the conversion factor 1,000 meters per 1 kilometer. Noting that those are equivalent terms. 1,000 meters is 1 kilometer, so I'm really just multiplying this by 1. I'm also going to multiply by 1 hour for every 60 minutes, and because I have hours in the numerator, and then in my original term I had hours in the denominator, hours is going to cancel, so now I'm at per minute. I need to change per minute to per second, so I'm just going to multiply by 1 minute for every 60 seconds. So I'm going to multiply by 1,000, divide by 60 twice, or it is the same as dividing by 3,600. And that's going to give me a initial velocity of 6.67 meters per second horizontally. That means that my x dimension original velocity is 6.67 meters per second. In the y dimension, my cliff diver starts from rest, from 0 meters per second. My final x velocity, my final horizontal velocity is going to be the same as the initial x velocity, because in the x dimension, there's no acceleration, and my base jumper is going to be moving at the same x dimension speed the entire time. In the y dimension, I don't know what the final velocity is going to be. And just looking at this problem, I don't think I'm going to have to know, because I know there's acceleration happening in the y dimension. I could calculate it because I know the amount of time that acceleration is being applied for. And in fact, this would be the easiest type of velocity acceleration time problem to solve, because I'm looking for final velocity, so it's just acceleration times time. But I don't need that for solving this problem. I will need acceleration, though. In the x dimension, acceleration is 0 meters per second squared. In the y dimension, it's negative 9.80 meters per second squared. And then finally, I'm given a time of 3.22 seconds, and that applies to both dimensions. That time has to apply to the x as the same as it applies to the y, because my object is moving in both dimensions in that amount of time. Okay, now, when I look at these two columns, I'm noticing that I know everything except for one value in the x dimension, and everything except for one needed value in the y dimension. I don't need that final velocity to calculate position. I just need original position, original velocity, acceleration, and time, all of which I have. So the point is, I can start with whichever dimension I want to as I solve this problem. There's not a particular dimension I have to start with. So we're going to start with the x dimension as we go through this. The equation for the x dimension is going to be this one, because these are the variables that I know from my table. And I'm just going to cross off what's going to be 0. Most importantly, there's 0 acceleration, so that entire final term crosses off. My initial position is also 0, and this simplifies to be a very simple equation, 6.67 meters per second times 3.22 seconds. And we would expect it to be this simple because I'm moving at a constant speed in the x dimension for a certain amount of time. My distance is going to be 21.5 meters. I'm just going to go ahead and plug that into my table now that I know what it is. What about the y dimension? A little more complicated, but certainly not hard. This is the equation. Is there anything that's 0? Well, my initial position and my initial velocity are both 0. So this equation is going to simplify to something very simple as well. Simply 1/2 a t squared. A is negative g, or negative 9.8. 1/2 times negative 9.8 is negative 4.90. I have to make sure that I square the time, 3.22 squared, and when I calculate what y is here, I find that it's negative 50.8 meters. Notice that that negative sign carries along. Would we expect that? Was my y position meant to be negative? Well, of course it was. It was below where I started. So I'm just going to go ahead and plug that into my table, and now I have everything I need to find the displacement of the jumper when the parachute deploys. Displacement is a vector, so it's going to have a magnitude and a direction, and I'm going to need to calculate it. How do I calculate it? Well, I need to make a right triangle. Here is my x displacement vector, my y displacement vector. They're at right angles to one another. If I add together my x displacement and my y displacement using vector addition, and notice that I have the directions laid out correctly, x is pointing to the right, y is pointing down. Also, I'm adding them by putting y at the head of the x vector. So I drew my x vector, I started with the tail of y at the head of that x vector. Now I'm going to draw my resultant, which starts at the tail of the first and goes to the head of the last. There's my resultant vector, and that's where my angle theta is going to be in this right triangle. Now, how are we going to calculate this? Well, I know x and I know y, so I could just use the Pythagorean theorem to solve this. I'm just going to note the correct values on my triangle. So the x is actually 21.5 meters, the y is actually negative 50.8 meters, and then let's calculate the value of the resultant. It's simply going to be x squared plus y squared, and then I need to take the square root of that according to Pythagorean theorem. Here's what that looks like. When I plug in my values, I find that the resultant value is 55.2 meters. But that's not all. To calculate a vector, I also need to include a direction. So I need to calculate the angle theta to report my displacement. For that, I'm going to use the tangent function. Tangent of theta is the ratio of the opposite side over the adjacent side in a right triangle. My opposite side here is 50.8, and I could plug in negative 50.8. And my adjacent side is 21.5. And I can calculate the ratio of the opposite side to the adjacent side is 2.363. But I don't want the ratio of those sides. I want the angle associated with that ratio. So the tangent of theta, the ratio of those two sides is 2.363. What is theta? To find theta, I'm actually going to have to find the inverse tangent of that ratio, and that's going to return the angle that's associated with that ratio. So I take the inverse tangent of both sides. The inverse tangent of the tangent of theta is simply theta on the left, and the inverse tangent of 2.363 is 67.1. I know my angle is 67.1 degrees. But that's not a degree measure that I'm going to report because that's below the x-axis, and I want from the positive x-axis counterclockwise. So I'm actually going to measure this angle here, which is 360 degrees minus 67.1 degrees. So all the way around to 360 degrees minus that 67.1 degree measure gives me 292.9 degrees. And that's going to be my final vector direction. And my final vector value is 55.2 meters at 292.9 degrees. I could have also reported that as 67.1 degrees south of east. Now that we have our answer, let's take a moment and just reflect on exactly what we're looking at here. These vectors are displacement vectors, which are related to the position or distance that an object moves. Okay, so we are dealing with vectors that are measured in meters, which is pretty atypical for vectors. It's very straightforward for us to measure and visualize position and distance and displacement. So oftentimes we don't use vectors to measure those things. We can, we just did, but a lot of times we're going to use vectors for more abstract things because they help us to solve more abstract concepts like velocity. We'll take a look at how velocity relates to this problem in just a moment. But another thing I want to do just to clear up confusion with vectors. So one of the things I just want to mention is pay attention to what your vectors are. These are vectors measured in meters. That means they are displacement vectors. So we're actually measuring position in space here. The other thing I want to point out is that when we graph this problem, it's going to have a very specific look to it that's the same for projectile motion problems. So here I'm going to bring in an x and y axis. And I'm also going to note the first thing we're going to put on our graph is the x-axis position. This is a position time graph, and we're going to start by graphing what's happening in the x dimension, which follows this equation. The x position is going to be the original position plus the amount of velocity times the time that has gone by. And if I were to put several of the actual points from this problem on this graph, it would look like this. Here's my x position points, and then I'm going to connect them all with this line. And notice that in the x dimension, there is a straight line position time graph. And I can calculate the slope of this line. The slope is actually the speed that the object was moving in the x dimension in this problem. In the y dimension, I'm going to use this equation. This is my parabolic equation. Keep in mind that for a horizontally launched projectile, there is no initial speed in the y dimension, and that means that my parabola is going to start either at a maximum or a minimum. Now, one thing I'm going to do, I'm actually going to flip around the sign on gravity. So instead of making this parabola go down into the negative positions, just to keep this graph simple, I'm going to flip it so that downward is positive and my y dimension parabola is going to point upward. So here's what that parabola would look like when I flip it over the x-axis. These are several points that would actually be on this parabola. Now notice that these are two independent graphs. They're not really related to each other, and the only reason they're on the same graph is because they're happening in the same time interval. But really, I could also draw these as two completely separate graphs, because this object, even though it's moving in the same time, the dimensions are being treated very differently. In the x dimension, this is moving horizontally at a constant speed. In the y dimension, it's being accelerated by gravity. So I've put both of these curves on the same graph. Many times you'll see this done with projectile motion. And the reason they're on the same graph, it is the same object. It's just two dimensions of motion of the object. You will just as commonly see each dimension split up into a separate graph. But now you can compare the motions, the graphical motions of the two dimensions. In the x dimension, the object is moving linearly. In the y dimension, it's moving parabolically. Also of note is that we are able to graph each dimension separately because the dimensions are independent of one another. All right, and what are we solving for in this problem? Well, we're looking at the motion at 3.22 seconds. So we're just asking ourselves on these two graphs, what is the position going to be when I analyze at 3.22 seconds? So I've got both of my functions, the equations already written out. Now I'm going to plug in 3.22 as my input time and see what I get as an output for my position. For the horizontal dimension, I find that the object at 3.22 seconds is at 21.5 meters horizontally, and then vertically, I find at 3.22 seconds, when I plug that value into my function, I get 50.8 meters vertically. And actually, remember, it was negative 50.8, but now I've redefined my y dimension so that downward is positive. Next, before we move on from this problem, let's take a look at a real-world example of what a cliff dive looks like. Now, this is not going to be this specific cliff dive, so don't expect the times and the distances to match up, but we're going to take a look at the projectile motion involved in a cliff dive. Also, please notice that this is a very far away camera shot, and also that the projectile, the person who's diving from the cliff, is doing a lot of rotating tricks in the air, so it's very difficult to keep track of where that person's center of mass is. But this is what the cliff dive essentially looks like. Notice the parabolic motion as this diver jumps from the cliff. Now, it's probably pretty difficult to pick out that that's parabolic. So let me prove it by showing you more of the video. And this time I'm going to put the points on the video as I go. I'm also going to show you what the vectors look like in the x and the y dimension. Again, keep in mind, this is a rough video analysis because we're so far back and it's so difficult to keep track of the center of mass. But we're going to do our best to keep track of what the velocity vectors look like. Can you imagine what the first velocity vector is probably going to look like? Keep in mind, this person is launching themselves horizontally from the cliff, so we should start with a horizontal velocity vector that is becoming more and more vertically downward, but at an angle, right? Because if you look, you'll notice that my horizontal components of my velocity vectors are essentially the same. They're a little different. Some of them are longer than others. And again, that's because this diver is rotating in the air. So sometimes as I'm clicking on what I assume is the center of mass, sometimes I'm a little bit too far forward, sometimes a little too far backward. But you can see that essentially there's this constant forward velocity. What's happening at a downward velocity over time, though? The downward velocity vector is increasing and increasing. And if I were to add these vectors together, and keep in mind, this isn't showing you vector addition. This is just showing you all of the vectors coming from the same point. But if I were to slide my vertical vector over so it's at the head of my horizontal vector and add these together, the resultant would be the blue vector pointing at an angle downward. And keep in mind what's going to happen over time. As this diver falls further and further, more and more velocity is going to be built up because of acceleration. And that velocity vector is going to be pointing more and more and more downward. The horizontal vector is going to essentially stay the same during the entire fall because horizontally this diver should be moving at a constant speed. Let's take a look at another example of this kind of motion. Maybe cliff diving isn't your thing. Maybe it's pretty unfamiliar to you. I'm guessing this will be much more familiar to a lot of people. What about throwing a basketball? Now, my video here is much, much better. Still not perfect. There's still some error in certain unknowns in the video, seeing as how I didn't set this video analysis up. I didn't use special recording equipment. So I'm still just doing my best to measure where a sort of blurry object is as it moves through this video. But let's take a look at this type of projectile motion. As it leaves the person's hand, only gravity is acting on the basketball from the arc from the person's hand to just the moment before it hits the net or the hoop. All right. And if I look at this with points, notice that there's that parabolic motion happening. And I can consider that parabolic in two ways. In the XY position map that we're looking at, there is a parabola there. But more importantly, for what we're doing in physics, if I were to graph the Y dimension motion over time, I would see that it makes a parabola with the position time graph as well. And then horizontally, just like we've seen time and time again in these videos, horizontally it appears to be moving at a constant speed, so linearly in the X dimension. All right, we're going to take a look at the vector view of this, just like we did with the cliff diver, and this one's a lot better. Notice that my X dimension vectors, as I place them in this video, are pretty much the same length. But what's happening to my Y dimension vectors over time? Notice that they're getting shorter and shorter until the ball reaches its maximum arc, and then they're going to turn around and start becoming longer and longer in the negative direction until I'm finished analyzing the motion of this basketball. Now, notice that the resultant is that my velocity is constantly changing as this ball arcs through the air. Why is the velocity constantly changing its direction? Well, keep in mind, the x velocity is not changing. The x velocity vectors are pretty much always the same. And this does a better job than the cliff dive because the basketball is an easier object to keep track of. Notice that my x dimension velocity vectors are essentially the same. Maybe some minor differences as I clicked in just a little bit the wrong spot, but you can see the pattern there. But what's changing my velocity overall, the reason that those blue vectors are changing is because the y component is changing. Because there's acceleration in the y dimension, there's change in velocity there, and it's changing the velocity of the ball overall as well when I look at this parabolic arc. The point is that the blue vector represents an instantaneous velocity at any point on this diagram. And we can measure that instantaneous velocity at that point by knowing what the x dimension vector at that point is and the y dimension vector at that point. We've been doing this a lot. We've been solving for the position or the speed at a specific moment in time in a lot of the problems that we've been working in physics. And then just to note that that instantaneous velocity vector is changing, but in a very predictable way. Let's see if we can calculate those values for one of these instantaneous velocity vectors in the video. Let's see if we can figure out what the initial speed and launch direction of the ball is as it leaves this basketball player's hands. So here we go. We're going to bring in our graphs from our video analysis. First of all, I'm going to bring in our acceleration time graph. Notice that this follows patterns that we would expect to see. First of all, in a real-world graph, we would expect there to be aberrations, but we would still expect to see a general trend. The trend I would expect to see here is that the acceleration in the x dimension should be around 0. That's the red curve on this graph, and notice that it does dip below and rise above 0 at points, but overall this graph trends toward hovering horizontally at 0. So this is what I would expect to see from a real-world acceleration time graph for constant velocity in the x dimension. In the y dimension, we should be around negative 9.8 at a constant value. So a horizontal line at negative 9.8. We could see negative 10 on the y-axis. And notice that this appears to pretty much stick around that negative 10 horizontal line. So this does show a pattern in the acceleration time graphs that we would expect to see. Constant 0 acceleration horizontally, constant negative 10 vertically. What about my velocity time graphs? Well, the velocity in the x dimension, that's red, should be constant, which is what we see. It's a constant velocity of somewhere around 4.1 meters per second. Notice that even my linear curve fit works out with a slope that's almost 0. It's very, very small. So this would represent a horizontal line. Now, I don't recommend doing linear curve fits on horizontal lines. The better way to do this is just to calculate the average of all of the points, but this one actually worked out pretty well. And then in the y dimension, we have a velocity that starts positive, but is decreasing at a rate of about negative 10 meters per second squared. Notice that my slope for this line is negative 9.77, almost negative 9.8. And it's decreasing at that rate until it gets to 0. So there's a point at which the y dimension velocity of the ball is 0 meters per second. That's at the highest height, the maximum arc. And then it becomes negative and continues to decrease at the same rate, but now in the negative region of the graph. So the ball is going to start accelerating downward and move at a faster and faster velocity downward. And we see that in our parabolic distance time graph for the y dimension as well. Notice here in this distance time graph, we see the time at which the ball reaches its maximum y dimension height at the maximum of the blue parabola, and then the ball begins to move downward from the direction that it came. In the x dimension, as expected, the red curve on this graph, we have a linear position time graph with a slope of about 4.1. That's the speed of the ball, 4.1 meters per second, and that 4.1 meters per second is persisting as the speed of the ball. There's no acceleration in the x dimension, and this is what we would expect to see from our video. What we analyzed, as we analyzed the curve in the video, we saw that there was y dimension acceleration due to gravity and x dimension constant speed. Okay, but what about my question? Can we use the data in these graphs to figure out what the launch velocity, that means speed and direction, of the ball is when it leaves the basketball player's hands? Well, let's just consider what we know. If I were to plot out my x and y components and add them together for that first point in the video, adding them together would result in the initial velocity vector that has a certain angle. So the direction of it can be reported as well as the magnitude. So what do I know? Do I know the initial x velocity? Well, I know the constant x velocity from these graphs is somewhere around 4.1 meters per second. And then can I figure out from these graphs what the initial y velocity is? There's a couple of ways to do that. The most appropriate way to do that would probably be to use the parabolic curve fit and look for the VO term. Remember, it's VOT. I see that VO value, which is the b in my quadratic equation for the parabola, is 5.087 or about 5.1 meters per second. And I'm just going to compare that to the y-intercept from the linear equation for velocity time, because the original velocity should be the y-intercept of my velocity time curve. Notice that in the y equals mx plus b equation for the velocity time graph, that b value, the y-intercept, is 5.071, which rounds to 5.1 meters per second. I'm fairly certain that the initial velocity of this basketball in the vertical dimension is 5.1 meters per second. And now that I have both of these values, I can calculate for the third side of this right triangle, which is the actual velocity magnitude that the ball launches with. And I can also solve for the angle, so I have that whole velocity vector. I'll use the Pythagorean theorem with the two known sides to calculate the length of the unknown side, which ends up being 6.5 meters per second. And then I can use trig relationships, in this case the inverse tangent of the opposite over the adjacent side from my angle is going to give me the actual angle of the ball's launch. So there's a few things that I know from this. I know that the ball was launched more vertically than horizontally with a degree measure of 51.2 degrees. That's going to be an angle that points more up than it points to the side. And I know that the initial launch velocity of the ball was about 6.5 meters per second. Now this was for a free throw shot. What about a three-pointer, which is a little bit further back than a free throw shot? What would you expect these velocities and the angle to be? Are they going to be significantly different? Okay, so just remember 6.5 meters per second here at about 51.2 degrees. Now let's watch a video of a three-pointer being shot. Notice it's a shot that's further back. And we could do the same thing to analyze this shot. Here's the arc of the ball through the air. Then using the tools of video analysis, I'm able to get these graphs. So first of all, you'll notice that this graph is a lot less certain than the previous one. The previous one clustered pretty close with its red curve near 0 and its blue curve near -10. This one has a lot more spread to it. I do see, though, that the x-dimension acceleration does tend to cluster around 0 horizontally, which means there's no acceleration in the x-dimension. And the y-dimension acceleration tends to cluster around -10 still. You could make the argument, I suppose, that this is a little above -10. More of the points are above -10 than below. But this is what we would expect to see in real-world data collected of a ball moving through the air through video analysis, even if the acceleration was constant in the y-dimension and there was no acceleration in the x-dimension. This gives a little bit of a clearer picture what's happening. Once again, we see that the x-dimension velocity tends to be pretty constant. And I'm not thrilled, again, doing a linear fit because you can see that this has a little bit more of a slope. But we could say that this slope is essentially 0. It's pretty close to 0. The y-dimension slope is what we would expect. It's going to be somewhere around -10 meters per second squared. In this case, it's -8.7. So that's right in the ballpark there. What we would expect from constant acceleration in the y-dimension due to gravity. Then finally, our position time curves show what we would expect. In the x-dimension, we have a linear change in position over time. So we would expect to see with a constant velocity. In the y-dimension, we see that we have acceleration. An acceleration of about -10 meters per second squared when you double the a value. Remember, that's 1/2 the acceleration according to our parabolic equation for position time. And then I see there I have an initial speed, a VO term of about 5 meters per second, 4.944. Now, if I go back to my previous velocity time graph, I'm just going to compare. Notice that the y-intercept of that velocity time curve is somewhere around 4.3. So I have a little bit of differing data here on what my initial velocity is. Is it somewhere around 4? Is it somewhere around 5? I'm going to take the value from the quadratic curve fit because that's the one that does the least amount of confounding math to calculate. So it's just calculating what the best curve fit is. It's not first of all calculating the velocities and then calculating a curve fit secondarily, which adds a little more error in. So I'm going to say that this has an initial velocity of 5 in the y dimension, and I can see that the constant velocity in the x dimension is about 4.2. So I'm just going to go ahead and make that triangle again. Remember, this is adding the x dimension vector and the y dimension vector to get the resultant vector showing the speed with which this leaves the basketball player's hand and the direction. So I get this velocity vector. And if I plug in the values I know 4.2 meters per second is my constant horizontal velocity, and 5 meters per second. I'm going to just use one significant figure here because I'm really unsure. It's different between the two graphs, but it's about 5 meters per second initial vertical velocity. And I can use these two values to calculate the unknowns. Like, first of all, I can calculate the size of the hypotenuse. Ooh, 6.5 meters per second. That number looks familiar. And then if I find this angle, I get about 50 degrees. Before we had an angle of 51.2 degrees for the free throw. Once again, I observe that this shot is more vertical than horizontal. So the ball is going to float higher than it's going to just move directly toward the hoop. And it's not that much different from previously, although this is a little bit more direct. It's a little bit more horizontal than the previous shot, which is somewhere around 51 degrees. So that one would have floated a little more from the free throw as opposed to from the three-point line. Now, are these significantly different? I would have liked them to be more significantly different. Actually, we see that the speed values for these two calculations were the same, 6.5 meters per second. Does that mean that the speed of the free throw shot was exactly the same as the speed of the three-point shot? Wouldn't the three-point shot have to be moving faster to make it to the hoop? And the answer to that is probably, but I can't detect a significant difference in the techniques that I used analyzing these two videos. So part of that is just that every time I make measurements, there's uncertainty involved. And there's a lot of uncertainty involved with video analysis because I'm clicking on points that might not be the actual point where the ball is, but I'm just doing my best to find those points. So my techniques here of measuring may not have been able to detect the difference, but there is something else going on here that could explain that these two values are so similar to one another, and that is, look at how these shots are carried out. Here's the free throw shot once again. Notice his motion as he makes that shot. Now look at the three-point shot again. Notice his motion as he makes the shot. A free throw is shot from the ground. The ball is high above the person's head, but it's shot from the ground. When you shoot a three-pointer, you can jump into the air, and that might make some of the difference. So some of it is probably uncertainty in the video analysis. If I had better measuring tools, I could probably detect what the actual speed of the ball is a little better, and we would probably find that in the three-pointer, the ball is shot with more speed than the free throw shot. But also notice that there are other factors at play here too. The height of the player is going to make a difference as well. And we found that the angle was a little bit more flat with the three-pointer as compared to the free throw, which is going to project the ball toward the hoop better. Okay, now let's consider a real problem involving this basketball player. But in this case, we're not going to do a free throw or a three-pointer. We're going to do a desperate half-court shot from 13 meters away from the hoop. The ball leaves the player's hands at 2.6 meters above the floor. The hoop is 3 meters above the floor. And the player is shooting the ball with an initial speed of 11.5 meters per second at 47 degrees. Now notice in this problem, we're given the initial velocity of the ball, 15 meters per second at 47 degrees. The question is, will the ball reach the basketball hoop? So now that we've done this in reverse and we figured out what the velocity of the ball leaving the player's hand was, let's now analyze the other way. We know the velocity leaving the player's hand. Let's see if it reaches the basketball hoop. And I'm going to start by setting this problem up. Here's my player, my basketball hoop. This is going to be the motion path that the ball follows. Okay, so this isn't a position time graph. This is a position graph. I'm showing my Y positions and my X positions. I'm going to draw it so that the ball goes 13 meters. The ball starts from 2.6 meters above the floor and it ends at 3 meters above the floor. And this is going to be the setup for my problem. Now, what are the things that I know? Well, from my diagram, I know a few things. I know that the original X position is 0 meters, according to my diagram. My original Y position is 2.6 meters above the floor. I'm going to say that my final X position is going to be 13 meters. So I'm going to say I know this ball is going to go 13 meters. But here's the thing. It would seem like my final Y position must be 3 meters, right? But actually, the question is asking, is the ball going to reach the hoop? Is the ball really going to be at 3 meters in the Y dimension when it goes 13 meters in the X dimension? So instead of saying I know it's 3 meters, I don't know. I'm going to just put a question mark. That's the variable I'm trying to find. And I'm just going to note right next to it, I'm asking myself the question, will it be 3 meters? Is it going to be just above 3 meters, so it's probably going to fall in the hoop? Or is it going to be way too high, way too low? Or even, is it negative? The ball has already bounced once off the floor at this point because it didn't even get close to making it. So there's a lot of values that Y could take on. We're going to see if it is at or above 3.0 meters. Now, do I know the initial velocity of the ball? Here's the thing. The difference between this problem and the horizontal problems is this part. In the horizontal problems, we knew the initial X velocity was whatever the X velocity was when it was launched horizontally. And the initial Y velocity was 0. Because when you launch an object horizontally or drop it, the initial Y velocity is 0 and then it accelerates due to gravity toward the ground. In this case, though, we have an initial Y velocity and an initial X velocity. Look, the ball is being launched upward, so it must have initial Y velocity for it to go upward for a little bit, and then as it's accelerated, it comes to rest at the highest point and then starts to fall back downward toward the hoop. Can we figure out what that initial Y velocity is? Why, yes, we can using vectors. Okay, so we know that the ball has an initial X and Y velocity, and the combination of those two is the same as the resultant. When I add together this X velocity vector and this Y velocity vector, it's the same. That expression Vx plus Vy is exactly the same as the expression of the vector V. You'll remember that we talked about that. We talked about how vector addition is stating an equivalence. And my equivalence is that my horizontal plus my vertical here is going to equal the actual velocity vector. I can use this because if I can find these two components, I know what my X dimension original velocity and final velocity are, and I will know what my initial Y velocity is. Let's see how this plays out. So I'm going to plug in the values that I know here and solve in the X dimension and then the Y dimension. I know that my X dimension vector is going to use the cosine formula. So now I'll rearrange that formula so I have a version of it that includes the values that are actually in that right triangle diagram. I'm going to solve V cosine theta is going to give me that X component value that I'm looking for. When I plug in the values that I know that my V value is 11.5, and the cosine of theta is actually the cosine of 47 degrees for this right triangle. When I plug that into a calculator, making sure I'm in degree mode, I solve and find that the X component, my initial and final X velocity, is 7.82 meters per second. Now, just a quick note, this is nearly a 45-45-90 triangle. So when I do calculate the initial y component, I'm going to find that that y component is going to be very similar to the x component value because it's almost the same. In a 45, 45, 90 triangle, it would be the same. This is like 47, 43, 90 triangle, so almost the same. The next thing I'm going to note before I move on to the y dimension, we're going to record this in the table, but I just want to note why I'm recording in the table what I'm recording. So here we're working in the x dimension, and in the x dimension I know that the speed is going to be constant all the way across. In other words, for each time interval, the x value of the distance that's covered, just the horizontal distance that's covered, is always going to be the same for each time interval. The speed in the x dimension is going to be constant, and therefore that 7.82 meters per second in the x dimension could be recorded for the initial speed and the final speed because there is no x dimension acceleration. All of the acceleration that's happening is in the y dimension because of gravity pulling downward on the basketball. All right, speaking of the y dimension, in the y dimension I'm going to use the sine formula instead of the cosine because I'm looking at the opposite side of my triangle, which is the vertical side. I'm going to rearrange that equation so that I'm plugging in values from our actual triangle, and then I'm going to solve for just that opposite side length. So that's going to be the same formula, except this time with sine 47 instead of cosine 47, and I am going to get something very similar, 7.84 meters per second. And again, where am I going to plug that in? Well, that's just the initial velocity. Because if you think about what's happening here, the ball is going to go up and come back down. And as it goes up and comes back down, it's constantly being accelerated in the negative direction. So it's not going to maintain a constant speed. From the moment the ball leaves the player's hand, it's going to be decelerating toward the ground. It's going to reach a maximum height, and then its velocity is going to become negative as it falls back downward toward the hoop. So that means that in my table, I can only plug in this value as the initial y. The final y is unknown. The final y velocity is unknown. And that's probably not something I'm going to need in this problem at all. I don't know what the y velocity is as the ball enters the hoop. But I do know that initially when it leaves the player's hand, it's 7.84 meters per second. And I know that because that's the component of that right triangle that I used. Acceleration is negative 9.8, and we don't know the amount of time, but we can solve this problem with the given information. It looks like we know almost everything about the x dimension, so that's where we're going to start, and then we can use what we find in the x dimension to help us solve for the y dimension. So let's do that. I'm going to look at our x dimension. The equation we'll be using is our position time equation and applied for the x dimension. And let's start by considering what's going to be 0. If my acceleration in the x dimension is 0, that gets rid of this entire last term. Also, my position in the x dimension starts at 0 as well. So this ends up being a very straightforward equation. We're going to use it to solve for time. So rearranging, you can see time equals my final x position divided by the velocity in the x dimension. Just plug in those values. 13 divided by 7.82 gives me a time of 1.7 seconds. That means that I figured out from the x dimension, moving at a constant speed of 7.82 meters per second, which we know was the speed from the initial velocity and angle, moving at that speed, it's going to take 1.7 seconds for the ball to go 13 meters. Now, the question is, in that 1.7 seconds, is the ball now 3 meters above the hoop? Let's consider the y dimension to figure that out using that 1.7 seconds, which applies to both the x and the y dimension. So in the y dimension, same equation, except this time we're going to apply it in the vertical instead of the horizontal. Also notice my acceleration is negative 9.8 meters per second squared, or negative g. I'm just going to go ahead and simplify this right away. Nothing is 0 in this, so I have values to plug in for all of these variables. And when I plug in values for all those variables and multiply and add and subtract to solve, I find that my final y position is actually 1.8 meters. And is 1.8 meters above 3.0 meters? It is not. This person missed the half-court shot. It was underthrown, so no points at the buzzer. Now you know how to solve projectile motion problems when a projectile is not launched horizontally, but has both a horizontal and a vertical component at an angle.